Hello, Professor. I'm Nitin. We are the Group 19 presenting the topic Smart Detection of Structural Deficiencies using Artificial Intelligence. Benchmarking automated computer vision for the building defect identification, improving the construction quality, safety, and reducing the inspection time and cost. Can you go to next slide? Yes. Introduction to the automated defect detection. Automation needed. Manual inspection are slow, subjective, and costly. Inspection methods. Computer vision often consistent and the fast defect recognition. What are the challenges? Complex defect shapes and driven materials for the complicated detection. What are the benefits? The benefits are automation enhance accuracy, reduces the human errors, and saves resources. Can you go to the next slide, Aditya? These are the introduction. Accelerating urbanization, necessity, robust, and infrastructure management. Aging structures assessment underscore the impact for the active data-driven management strategies, ensuring public safety, hanging up the continuous monitoring and the preserve of the built environments. Can you go to next slide, Aditya? For the AI-based inspection systems. Manual inspection practice are the labor-intensive, subjective, and pronounced for the inconsistent. Human limitation result in the variability, inconsistent, evacuated operational costs. Artificial intelligence provides scalability, objective, repeatable assessment mechanism. Thank you, man. Next, my teammate Sham will continue.
Coming to the problem statement, the problems we address is the traditional inspection suffers from the human errors, inaccessibility, and delayed detection, which can lead to the increased reduced costs and safety risks. Our main objective is to design a resilient AI-based system capability of early and accurate defect diagnosis. Our research, coming to our research goals, develop an autonomous defect detection categorized frameworks, benchmark deep learning models, and improve detection accuracy across varied real-world conditions. For this, we built a conceptual framework that integrates the convolution neural networks and vision transformers, validated through a curated data set of structural anomalies. If you see the dataset, we use the deep BD3 dataset, which contains around 3,965 exactly annotated images of various defect types, including major cracks, peelings, spellings, algae, and more. To push the models redundance, we applied a data augmentation techniques such as horizontal flipping, brightness, and contrast adjustments, and rotational transformations, expanding the dataset out to about 14,000 images. This is the this is the few samples we used in our project. Thank you. My friend will continue.
Okay. Now we'll look into the data pre-processing and the transformation pipeline. So here we have just splitted the dataset into three parts, which is the training part, testing part, and validation part. For the validation part, we have given 20%. For the training, we have given 60%. And for the testing, we have given 20%. In the training phase, we can see that we have randomized the images to the 224 to 224 pixels, and we have done the normalization as well. And in the validation phase, we have consistently resizing the and center the cropping images, and we have used standardized normalizations across the data sets. Now we will look into some of the models which we have employed in this in this entire project. For this project, we have chosen three models, which is VGG16 and AlexNet and Vision Transformers, which is the which is non-CNN based architecture. Now we'll just look into the what the models exactly is, and I'll give you an overview of each of the model. First, we'll go through VGG16 architecture. It's an deep CNN based architecture which uses 3 into 3 kernels, and after that, like, it uses 13 convolutional networks with 3 fully connected networks layers. Next comes the AlexNet architecture. It's also one of the standard-based CNN-based architecture, but it has 5 convolution networks, which consists of 3 fully connected layers. And it also has an introduced ReLU activation and dropouts. It has a foundation to modern deep learning in the vision tasks. Next, we comes about the vision transformers, which is a game-changing model in this image classification sector. It was launched recently by Google, and it has proven itself working better with large data sets. For the transformer based, it's a non-convolutional architecture based, and it splits the images into patches and embeds them linearly, and it uses a self-attention to capture long range dependencies. That's the reason it works better with the large scale data sets and gives us the better results when compared to the standard CNN based models. Next, my friend Saket will continue.
Uh, Hello, Professor. Uh, Now let me go through the training, experimental design, and results. Before that, uh, I'll just tell you the basics of performance evaluation matrix. Uh, on that, first is accuracy. Accuracy is the proportion of correctly classified instance. Next, precision. It is the proportion of true positive predictions among positive calls. Next is recall, which is the proportion of positive identified among all actual positives. And finally, F1 score. It is the harmonic mean of precision and recall, balancing their trade off. Next slide, please. Yeah. Here in this model, we have we have fine tuned the pre-trained models by adapting their classification heads to recognize 7 defect classes. Training was carried out on GPU accelerated platform using TensorFlow and PyTorch. With these key configurations like optimizer, we have used Atom. The learning rate was 0.001. The batch size was 32, and the number of epochs we have used is 50. We have evaluated the model using accuracy, precision, recall, and F1 score. Now, coming to the results. Uh, Now we can see the training and validation accuracy of the VGG result. VGG16 achieved the test accuracy of 83.59%. And next, AlexNet, which has scored uh, yeah, the AlexNet model has scored the accuracy of 88.01%. Next. Now here we can see the results. The vision transformer outperformed the both CNN model, confirming its powerful ability to model both local and global features for structural defect classification. Now my friend will continue.
Coming to the experimental design, we have used the TensorFlow and PyTorch as the frameworks, and the hardware. We have used GPU accelerated computation platforms. And for hyperparameter configuration, we have used Atom app there as the optimizer and learning rate as 0.001 and batch size 32. And the number of epochs we have used is 50. The key experimental outcomes are the vision transformer achieved superior classification performance, and the while VGG16 and AlexNet established strong CNN benchmarks. For future research, Uh, we can deploy UAV-mounted imaging system for wider defect detection, and we can develop real-time monitoring systems with automated alerts, and we can expand the dataset taxonomy for more comprehensive defect coverage. And in conclusion, AI frameworks present a transformative approach to infrastructure maintenance, improving safety and efficiency. Thank you.